Welcome all. So today we will continue with the course. Today we will be looking into the analysis and design methods. So let us start the course. Okay. So the response to the shock loading or the pulse loading excitations. Okay. So a system responds to such pulse excitation and it does not reach the steady state condition, and the effect of the initial condition must be considered whenever we are dealing with the shock or pulse type of loading. Okay. The response of the systems to such pulse excitation can be determined by one of the several analytical methods. There are different of them, so we can choose any of them. We have the classical method by solving the differential equations. We can evaluate the Duhamel integral, and we can also express the pulse as a superposition of two or more simpler function, of which response solutions are easily available. Okay. And in all these things, the damping has little effect on the pulse excitation. Okay. So let us see how to deal with the pulse excitation. Okay. So as we have seen, okay, if we have a realistic system, okay, let us say we have a beam, okay, and let us say this beam is a part of a structural system. Okay. So this beam is part of a structural system. Okay. So this is a representation of a real life example. Okay. From there we take into the equivalent mathematical formulation. Okay. So we will make our beam. Okay. Normally we make our beam as a Euler-Bernoulli beam. Okay. What is known as the Euler-Bernoulli beam formulation, and the boundary condition we can approximate using the simply supported condition, or we can approximate using the fixed condition. Okay. Depend upon the type of fixity. Okay. We can either have simply supported condition or we can have the fixed condition. Okay. So from there onwards, okay, once we have this beam, okay, once we have our beam, okay, let us say we have approximated using a simply supported condition. Okay. And let us say we are dealing with a loading, okay, which is assumed to have uniform distribution over the entire length of the beam. Okay. As we have seen in case of a blast loading, we assume that a planar load, the wave is transferred in terms of a planar load to the entire system. Okay. So this can be a representation of a uniformly load. Okay. And the time history, okay, let us say if it is a pulse, the time history can be represented by the magnitude and the time duration of the pulse. Okay. So this is the time history representation of the force, and this is the spatial distribution of the force. Okay. So in this case, okay, the system is going to vibrate, okay, and we are expecting that the maximum vibration, okay, the maximum magnitude of the displacement is occurring at the center. Okay. So we choose this thing as the degree of freedom. Okay. So the vertical displacement at the center we are choosing as the degree of freedom, and in this particular case the maximum response will be covered by the first mode. Okay. So we are choosing this as the first mode. Okay. Mode 1 is our choice of mode, and the degree of freedom we are choosing at the center because we are expecting that the maximum displacement is occurring at the center. Okay. So we have chosen our degree of freedom, we have chosen our mode shape. Okay. From there we make our shape function. Okay. So the numerator part of the shape functions is the deflection equation. Okay. It is the deflection equation, and the denominator part is the deflection equation evaluated at y, the deflection equations y evaluated at x equals to L over 2, okay, at the center in this particular case. Okay. So once we have our shape functions, we make our equivalent mass, equivalent stiffness, and equivalent forcing function. Okay. So we already have seen the formulation for this. So 0 to L integrated mass per unit length, okay, stiffness again evaluated over the entire length, okay, and the forcing function. Okay. Okay. So in this way we formulate our equivalent mass, equivalent stiffness, and equivalent forcing function. Okay. So once we have this thing, okay, then we have our system, equivalent mass, equivalent spring, and equivalent forcing function. Okay. And the degree of freedom we are taking at u. Okay. And what u is doing is that u is representing the vertical displacement at this particular point. Okay. And this is our forcing functions. Okay. So once we have this system, we write down the free body diagram of the system. Okay. So this is my forcing function. Okay. This is the chosen degree of freedom. Okay. So, we are using the D'Alembert's approximations. So, we will have our pseudo acceleration, okay. Okay. Then stiffness, okay. We also have the damping part, but we are ignoring the damping part, okay. So, if we write down the equation of motion, so this will be our equation of motion from this free body diagram, okay. So, this is the free body diagram. So, from the free body diagram, this will be our equation of motion, okay. Initial condition, we are assuming that the system is at rest, okay. At time t equals to 0, the initial displacement is 0, and at time t equals to 0, the initial velocity is 0, okay. So, this is how from a real life beam to a mathematical approximation, from a mathematical approximation to a single degree of freedom approximation using the shape function, from there the equivalent mass, stiffness and the forcing function, from there the free body diagram, and from the free body diagram we write down the equation of motion, okay. And now we will try to solve this thing, okay. So, as we know, the analysis will be in two phases, okay. Here till time t equals to Td, the force is acting on the system, and after time t greater than Td, there is no force in the system, okay. So, that is why we are saying that the analysis will be organized into two phases. Force vibration phase, when the system is responding to the application of the force, and the free vibration phase, okay, once the force, effect of the force is not there, then the system is basically behaving in a free vibration phase, okay. Now, we will see how to analyze for the force vibration phase and the free vibration phase, okay. So, we have already seen the equation of motion, okay, and here we are representing it by the equivalent mass, equivalent stiffness and the equivalent spring, okay. So, response of this system, okay, the total response of this system is broken down into two parts, okay. U particular plus U complementary, okay, U particular plus U complementary, okay, or U transient and U steady state, okay. It means the same thing. In the differential world, we talk about particular solution and complementary solution. In the physical representation of this thing is the steady state response and the transient response, okay. So, we will see how to deal with how to evaluate these two quantities, okay. The complementary or the transient response is the response of the system without the effect of any external force. The particular or the steady state response of the system is the response of the system when the system is acted by an externally applied loading, okay. So, if we look for the formulation of U complementary or U transient, okay, it will be given by A cos omega n t plus B sin omega n t, okay, where omega is the frequency of the system. We calculate A and B using the initial condition, okay. U steady state depends upon the signature of the system, okay. So, whatever is the forcing function, so this one is the signature of the system, okay, this will come from the system, the complementary or the transient part, and this will come from the externally applied force, okay. So, here the forcing function is P star, so it will be divided by K star, okay. So, that will give me the steady state response, okay. So, for this particular case, if we are looking into the phase where the forcing function is acting, then the total response will be the sum total of these two, okay. It means that A cos omega n t plus B sin omega n t plus P star time dependent part divided by K star, okay. And when we apply the initial condition, okay, U at time t equals to 0 and U at time velocity at time t equals to 0 is 0, okay. That means the system is starting from the rest. From there we can calculate the constants A and B, okay. So, once we do all this exercise, okay, once we evaluate everything, okay, what we will get is this solution, okay. We will get the solution like this, okay. So, this will be the solution, okay. So, this is the total response of the system, okay, and it is normalized by UST naught, okay, when it is just representing the static deflection, okay, the thing from the static deflection, okay. So, we have the solution for the, so this is how we calculate the solution for the forced part, okay. After this thing, what happens here is that the after time t greater than Td, the forcing part is removed, okay. It means that in my equation of motion now, okay, this thing has become 0, okay. The forcing function part is removed. Okay. So what remains is just the transient part. Okay. So the only transient part will come into picture. Okay. So now the solution of this system, okay, after time t greater than td, it will be ut equals to a1 cos omega n t minus td. Okay. We are looking after the time, and b1, okay, cos omega n t minus td. Okay. And the initial condition for this response will be the final condition from the previous one. So if we put here time t equals to td, okay, so whatever u at time t equals to td we are getting, that we will call it as u naught. Okay. And we will use this initial condition, we will use this final condition as the initial condition for our next phase. Similarly, the velocity at time t equals to td, so u dot naught. Okay. So that final velocity we will use as the initial condition for this system. Okay. And then we will calculate the response of the system, the free vibration response of the system once the load is removed from this surface. Okay. So if we do all this, we have the two response of the system. Okay. The response in the in the forced vibration phase means response here, and the response in the free vibration phase means the response out here. Okay. So this is how we will calculate the total response of the system for the two phases, the forced response, the response of the system in the forced phase, and the response of the system in the free phase. Okay. So this is the same thing, the initial condition that we are going to use. Okay. So this is how we are going to solve this problem. Okay. Okay. So same thing. Okay. So we will get the response of the system for the phase when the forcing function is removed. Okay. So this is the simplified form of this thing. Okay. So if we simplify all these things, we see that the response of the system is a function of time of loading as well as the natural frequency of the system. Okay. So ut becomes a function of ust naught, okay, meaning a function of the static response and the ratio of the time of the applied loading and the frequency of the system. Okay. So the response is a function of the static response and the ratio of the two time components, okay, time of the loading and the natural frequency of the system. Okay. So the entire thing we can draw like this. Okay. What we can do is that we can represent ut, okay, ust naught, okay, as a function of td divided by tn. Okay. So for different values of different ratios of time duration of loading and the frequency of the system, we can represent it using this curve. Okay. And this curve we can use as a design curve. Okay. And in order to obtain, okay, this curve, what we need to do is that we need to calculate the maximum response of the system. Okay. So here in the earlier phase, okay, okay, we have the response of the system in the forced phase, we have the response of the system in the free phase. Okay. So if we differentiate, okay, what we can do is that we can calculate the maximum response of the system in the two phase, and from there we can also calculate the absolute maxima response. Okay. And then we can plot this absolute maxima response also, okay, and then use this thing as a design curve. Okay. So here what we are seeing here is that depending upon the different time of the loading, okay, the ratio of the different time of the loading with respect to the frequency of the system, we see the behavior of the response of the system. Okay. So what we observe is that the nature of the response is seen to vary greatly by changing just the duration of the pulse. Okay. If we change the duration of the pulse, okay, here we see that the frequency of the system is remaining constant. Okay. For a given system, okay, the frequency is always constant. Okay. So if we keep on changing the duration of the pulse, okay, we can see that the response of the system is changing from non-oscillatory to an oscillatory response. Okay. No matter how long the duration, the dynamic response is not close to the static solution. Okay. So whatever happens, okay, the maximum response will never be close to the static solution, okay, because the force has been applied suddenly, okay. So the dynamic solution will always vary from the static solution, okay. When the force is applied to the structure, the system oscillates about the shifted position, okay. So the system is oscillating with respect to the static deflection position, okay. So the oscillation is always with respect to this static deflection position, okay, at its own natural period, okay. So after the pulse ends, the system oscillates freely about the original equilibrium position at its natural period, okay. So once the effect of the force subsides, okay, the system is going to oscillate with its natural frequency, okay, and there is no decay in motion because we have ignored the effect of the damping, okay. If this ratio, okay, Td by Tn ratio is a multiple of 1 to 3, the system stays still in its original undeformed configuration during the free vibration phase, okay, because the displacement and the velocity of the mass are 0 when the force ends, okay. So these are the things what we can observe by changing the duration of the loading, and this is how the system is going to behave, okay. So this was a case for a pulse response. Similarly, we can deal with the other response of the system, okay. So over each of the two phases, okay, fixed vibration phase and the free vibration phase separately, the maximum value of response is determined, okay. The larger of the two maxima is the overall maximum response. It means that if the system is vibrating in two phases, okay, forced vibration phase and free vibration phase, okay. So we are calculating the response of the system, okay, in this phase, and we are also calculating the response of the system in this phase, okay. After that, what we can do is that we can calculate the maximum response in the free vibration phase, and we can calculate the maximum response in the forced vibration phase, okay. So and out of these two, whichever is the absolute maxima, okay, that is the absolute maximum response of the system, okay. The larger of the two maxima is the overall maximum, okay. The number of local maxima or peaks that develops in the forced vibration phase depends upon ratio of Td over Tn, okay. So how many maxima occurs, okay, that will depend upon the ratio of Td over Tn, okay. More such peak occurs as the pulse duration lengthens, okay. As the duration of pulse is increasing, we can see that we are observing more number of maximas, okay. The first peak occurs at T naught equals to T naught over T with the deformation this much, okay. It means that my dynamic deformation, okay, here is twice the static deformation, okay. The displacement at the end of each end of the pulse is given by this equation, okay. So similarly, we have evaluated this equations in the previous phase, okay. Continuing from the earlier observations, the maximum deformation during the forced vibration phase from equation A and B can be expressed in terms of the deformation response factor, okay. So what we are trying to do is that we are trying to make a ratio, okay, we are trying to make a ratio of the deformation with respect to the static deformation, okay. So in the free vibration phase, the system oscillates in simple harmonic motion given by equation, earlier equation 2, okay, which is represented by here and which can be reduced through here, okay. So here the corresponding deformation response factor is given by this quantity, okay. So the overall deformation response factor is nothing but the dynamic divided by the static deflection phase, okay, that is given by this equation, okay. So here we can see a plot, okay, of the response factor with respect to the change in time period of the loading with the ratio of the time period of the structure, okay. So a plot which shows the maximum deformation of a single degree of freedom system as a function of the natural period Tn of the system or a related parameter is called the response spectrum, okay. So this is called the response spectrum, okay. So this curve, the outer curve is the forced response spectrum, and this is the free response spectrum, okay, and this is the overall maxima, okay, because the overall maxima is occurring here. So this is the total envelope of the response spectrum, okay. So this response spectrum we can use for the design of the pulse type of loading, pulse or shock type of loading, okay. So what we can do here is that we can choose the signature of the system given by Tn, we can get the time period of the loading, and from there we can calculate the maximum response of the system, and then if we multiply by the static component, that is P star over K star, okay, we will get the absolute maximum response of the system. You will get the Umax absolute. Okay. So, this is how we can make the response curve for the pulse loading and use it for the design purpose. So, let us do one example, okay, where we will try to solve this problem. Okay. So, in this particular example, we have a one-story building. Okay. So, one-story building we are representing by this framing system. Okay. So, this has been idealized as a 12 feet high frame. Okay. So, the height of the structure is 12 feet with 2 columns hinged at the base. Okay. There are 2 columns and they are approximated as hinge. Okay. The boundary condition is expressed as a hinge. Okay. And there is a beam is connecting the 2 columns and the beam is assumed to be rigid. Okay. It means that whatever is the deformation at this end, similar deformation will take place at the other end. Okay. And it has a natural period of 0.5 second. Okay. The time period of the structure is been given as 0.5 second. Okay. Each column is made up of a standard American section. Okay. So, it is a wide flange section having the properties W8 cross 18. Okay. So, these properties are given in the corresponding steel tables. Okay. Its properties for bending about its major axis are the second moment of area is given. Okay. The value of S is given. Okay. And the value of modulus of elasticity is given here. Okay. So, all the corresponding values that can be used are given here. Okay. So, here we will ignore the damping. So, the damping is ignored. We need to determine the maximum response of this frame due to a rectangular pulse of amplitude 4 kips. Okay. So, the maximum amplitude is 4 kips and time duration Td is 0.2 second. Okay. So, P naught is given, Td is given, okay, and the structural parameters are given. The response quantities of interest are displacement at the top of the frame and maximum bending stress in the column. Okay. So, we need to calculate the maximum deformation at the top and the bending stress in the column. Okay. So, we will see how to deal with this problem. Okay. So, we have been given Td equals to 0.2, okay. Tn is 0.5 second. Okay. So, first of all what we do is that we evaluate the ratio of Td over Tn. Okay. So, we put the value of Td and Tn. So, we get the ratio of 0.4. Okay. We know the equation for the maximum response. Okay. So, equation for the maximum response is this one. Okay. So, from there we calculate the maximum response ratio. Okay. What does it mean? It means that during the loading, okay, when the system is subjected to this forcing function, okay, the absolute maximum response, okay, in the forced vibration case as well as in the free vibration case will be 1.902 times the static deflection. Okay. It means that the Umax absolute equals to 1.90 times U static. Okay. And U static we can calculate from the P star and K star. Okay. So, P star is given by 4, okay, and K star we need to calculate. Okay. So, here what we were asked, okay, we were asked to evaluate this system. Okay. So, what is the response of this system? Okay. So, the mode shape we are assuming as the first mode, okay, in the cantilever mode, and we are taking degree of freedom at the top. Okay. So, if we go by our logic of defining the stiffness of the system, okay, the stiffness of the system is the amount of force required to get a 1 unit deflection, okay, at the chosen degree of freedom. Okay. So, the amount of force required. Okay. So, the deflection at the top for a cantilever will be given by P L cube over 3 EI. Okay. So, P equals to delta 3 EI over L cube. Okay. So, if we take delta as unit, okay, then the force required, okay, to cause this unit deformation, okay, will become my stiffness. Okay. So, my stiffness is this quantity. Okay. 3 EI over L cube, okay, using our simple static approximation. Okay. So, here stiffness has been given here. Okay. So, then the static response becomes the value of the forcing function, that is 4 kips, okay, divided by my stiffness value, which is this much, it becomes 1.07 inches. Okay. So, the maximum dynamic deformation becomes the quantity, the response quantity times the static deflection. Okay. So, 1.902 times 1.07, 1.902 times 1.07. So, this becomes 2.04 inches. Okay. So, we have solved one part. Okay. We have solved the displacement at top of the frame. Okay. Now, we will try to calculate the bending moment. Okay. So, how to calculate the bending moment? Okay. So, we will use the same formulation here. Okay. So, our quantity of interest was the maximum bending stress in the column. Okay. So, in order to calculate the maximum bending stress, okay, we need to calculate the bending moment, and from the bending moment we will be able to calculate the bending stress in the column. Okay. So, the bending moment, okay, that is occurring in this column, okay, it has been given by this equation. Okay. So, u naught becomes this value. Okay. It is being said that normally how we used to calculate the bending moment. Okay. We used to calculate it using by the bending stiffness, okay, bending stiffness times the deflection. Okay. So, here we are using the same equation. Okay. This is the bending stiffness times the deflection. Okay. So, from there we are calculating the bending moment. Okay. Once we have the bending moment, okay, we divide it by S of the section. Okay. S is nothing but Ix divided by H over 2 of the section. Okay. And from there we calculate the bending stress in the system. Okay. So, this is how we use the formulation in order to calculate the maximum deformation. From the maximum deformation we calculated the bending moment, the corresponding bending moment, and from the bending moment we calculated the bending stress in the system. Okay. Okay. So, continuing ahead. So, what we could have done is that we could have used the chart also, okay, chart of Td divided by Tn. Okay. So, using this chart, okay, so Td over Tn was 0.4. Okay. So, we come to 0.4, okay, and we look for a value where zeta equals to 0. Okay. It means that this curve, okay, and from here we can also read out the value of my ratio of Rd, which is nothing but U max absolute divided by U static. Okay. So, this is nothing but the representation of this curve. Okay. So, here it will come to be approximately 1.9, same as before. So, 1.9, and then from here we can also calculate my U static. So, U static is nothing but my magnitude of forcing function divided by the stiffness function. So, this we know, multiplied with the Rd, and we will get the U max absolute. Okay. So, we can use the formulation also, or we can use the design charts, okay, that are been given in various books, or we can use the design charts that are a part of our TM also. Okay. They are in TM 53900 also, UFC 340 also have those charts. So, depending upon any of those available methods, okay, we can calculate the maximum response. Okay. So, once we have the maximum response, what we do is that we use the theory of the equivalent static force, okay, what we have learnt already. Okay. So, it means that let us say we have a beam. Okay. Okay. We have a beam applied by a uniformly distributed load, okay, and it has a certain time variation. Let us say the time variation is in terms of this pulse only. Okay. So, then what we can do is that we can choose the degree of freedom. So, in this case we can choose degree of freedom at center, vertical degree of freedom. So, y vertical at center, okay, and we can choose the first mode, okay, and from there I can calculate my m star, k star and p star either from the design charts or from the parent equations. Okay. So once I have my value of m star, k star, p star, I can calculate my omega n, okay, root over k star over m star, okay. Then I can correspondingly I can calculate my Tn, okay. So I have my Tn, I have my Td, okay. So then I can use my design chart and calculate my Td over Tn, okay. And depending upon how much damping we are assuming, okay, we can take that particular value, okay, and then we can read out the value from this chart, okay. So we will have the value of Rd. Rd is nothing but U max divided by U static, okay. So U static we will calculate using P star over K star, okay. So we have our K star, P star, we will calculate our U static, and from U static we can calculate our U max, okay. So once we have our U max, what we say is that we will ignore the effect, we will ignore the cause for this deflection, okay. We will just look into the effect. Effect is my U max, okay. Now we will argue that this U max has occurred due to an equivalent force, okay. So this U max has been caused by an equivalent force, okay. And we know the deflection equation. We know that for this particular case PL cube over 48 EI will be my deflection, okay. So this will put as U max, okay. So P will be equal to U max times 48 EI over L cube, which is nothing but my K star, okay. I can use my K star also. So U max times K star will be my P equivalent force, okay. So I will have my P equivalent force out here, okay. So if I have my P equivalent force, I can redraw this system. So I have my P equivalent, okay, and from my P equivalent I can calculate the stresses at any given section, okay. So I can calculate the maximum stresses at the center out here, okay, because I know my bending moment will be PL over 4, okay, and from this bending moment I can calculate my bending stresses, okay. M over S will be my bending stresses, okay. So using the concept of equivalent static force, okay, applied to these equations, I can calculate all the quantities of the response, okay. So this way we can solve for the maximum displacement quantities, we can evaluate our maximum bending moment, we can calculate the maximum bending stresses, and so on and so forth, okay. So practice the examples and I will stop out here. Thank you.